I had a couple of questions during the break. One was regarding stability and invertibility. What does it mean to have roots inside the unit circle? I just made the simple one just down here in the corner, 1 minus phi b. To solve that equal to 0, I insert, z minus 1, z inverse, I insert that as b. And then I solve this equation and find that z equals 1 over phi. So to be within the unit circle, what has to be fulfilled? Well, phi has to be less than or equal to 1. So that means an AR1 process is invertible if, is stable, stationary, if phi is less than or equal to 1. Less than 1, to be strictly inside. And for the other moving average process, well, you end up solving a second-order polynomial, which is not so difficult. I had a question also regarding, well, now you have some data. I want to identify which model is actually this. What should I use? And that's the topic from next week, or the week after. So that's something we'll get back to. Today we'll look at the, you can say, the theoretical properties of these processes, and then we'll get back to, well, now we have data. How do we proceed from there? So this was the so-called autocorrelation. And I was speaking too much during the break, so I'll have to wipe out now. So the next thing is we identify that you have an exponential tail here, and you have this up here. When k becomes larger than the order of the moving average model, the autocorrelation is 0. We also have what is called the partial autocorrelation function, which is similar. And I just need some space. So what does this mean? It means that you look at the correlation between yt and yt minus k, conditioning on what is in between. So phi kk is the correlation, not the covariance, but you of course calculate the covariances first and then normalize. Correlation between yt and yt plus k, given that you have all the in-between observations, yt plus 1, comma, dot, dot, comma, yt plus k minus 1. So it's a conditional expectation that you have to use. And then we're back to pretty much what you did earlier on. Now, I ran out of battery. So what does that do for the different processes? The nice thing is for the AR1 process that we have here, we only get one thing that is significantly different from 0. We don't define it for lag 0 because you cannot really condition on anything. And the lag 1 is the same as the autocorrelation because there's nothing between yt and yt plus 1. But from lag 2, you can say, what is the correlation between yt and yt minus 2 if you know yt plus 1? Oh, sorry, yt and yt plus 2 if you know yt plus 1. If you go back one slide, well, what is the correlation between this one and that one if we know the one in between? Basically, we are, come on. Basically, we're looking at this one down here, where we condition that we know yt minus 1. So we should not do this expansion here. We should just stop here and say, condition that this is a constant. This is known. Then we are left with what is the covariance between epsilon t plus epsilon t and yt minus 2, which is 0. So that's the definition of the partial autocorrelation function. I'll just swap these batteries. The next thing is the inverse autocorrelation function. Basically, if we have a process yt, where it's defined as phi of b times yt plus theta of b on epsilon t. If we then take the inverse of both these polynomials and define the dual process zt by this process here, it's not something that we'll use a lot. But if you look at the autocorrelation function of the dual process, it's quite similar to the partial autocorrelation function, because you flip the sequence around, so to speak. So we will, in this course, use the partial autocorrelation function as the complementary thing to the autocorrelation function rather than the inverse autocorrelation function. But this is just so that you know that the other thing exists and what it means. Well, non-stationary processes. It's quite easy, I think, to see which one is non-stationary here, right? So what do we do about these things in general? What is the definition of stationarity? Do you recall? The distribution is invariant to changes in time, indeed. Which is true for one of these two, not the other, right? Okay, I'm in bad luck with batteries today. So, different types of non-stationarity. What can we do? Well, we can look at long-term trends at the top here. It's quite similar to something you've seen before. We can also have a periodic trend like this. It's also a non-stationary because, well, it depends on where you are in time, what the difference is. And you can have a general time-varying behavior, like this one down here, where there's no clear pattern. So we'll define an extra class of models where we say that we have not just the ARMA class, but we have the ARIMA class. And the I is for integrated. And what we do is that we introduce difference operator on yt, and then we define a new process, a new stochastic process, wt, and then if we have an ARMA model for wt, we call it an ARIMA model for yt. So all that is in here is that you have a different operator involved in here as well. So it's just to say that the definition of the ARIMA model, and we'll call the orders P, D, and Q. That is, you have first a phi polynomial in B, and then you have nabla to the D power on yt equals a theta polynomial in B on epsilon t. And this is order Q, and this is order P. Regarding stationarity, we have the same question. We just have to look at this here, including the difference operator. And if we are to solve something where we are already kind of multiplied it out in things that you multiply together, we know that we can find the roots. It's finding the roots of this part and this part. Solving 1 minus z inverse equal to 0 is not so difficult, right? Z equals to 1. So what does that mean? We have d roots because we have a d times differencing here in just 1 plus 0i, if we kind of consider imaginary things we will need in a moment. And if the phi polynomial here is stationary, so if the ARMA process that we defined for Wt here is stationary, then all the remaining roots are inside the unit circle. So far, so good. Should we just make a small example? Nah, skip that one. The next level of complexity, we're just talking about multiplying polynomials together, is for the other non-stationary processes we looked at before, we had a seasonal pattern. So how do we deal with that? One way is to do so-called seasonal differencing, or making a model for the season as well. So we'll introduce an extra set of polynomials, uppercase P, D, and Q, where we have the seasonal differencing operator, which is 1 minus b to the s power, where s is the season. Say if you have something that you observe every month, then s will typically be 12. And then you will make a model. You say if you have uppercase d equal to 1, lowercase d equal to 0, what you model is effectively how is now different from last year at the same time, which could make a lot of sense in many models. And all we get when we multiply things out is that we add an extra polynomial here. We have an uppercase phi for the seasonal part. We have a seasonal nabla, and then we have an uppercase theta for the seasonal moving average part. So all that we have is just a more complex polynomial. Typically, you won't have all of these things in play in one game. That becomes maybe too complex. And what we are, in statistics, what we generally want to do is to make simple models. We want to find the most simple model that adequately describes the data. When we get to real data, that's what we're aiming at. So right now, we're just figuring out what can we do with these different things. Stationarity is quite similar to before. You solve, this one was for the ARMA model. For the seasonal AR part, you set to the minus season, where you up here had phi of b to the s power, then you just have set to the minus s power. So it's the same procedure as before. These were from the nabla for the difference operator. We have 1 minus z inverse to the d power. This again gives us d roots in 1 on the unit circle. And the last one down here, 1 minus z to the minus s power equal to 1. If we solve that, that will give us s points placed around the unit circle. Say s is 2, then you end up solving z equals minus 1. That gives us I double root there. So we have d times s roots distributed along the unit circle. So we have the case d, lowercase d and uppercase d equals to 0, then we're considering things to be stationary. At least that's the assumption. Now, one such seasonal model could be to make a seasonal AR1 model, as defined here. So it's a season 12. It only has one parameter, so therefore it's a seasonal AR1 model. If we were to calculate the autocorrelation function for this one, well, what would we do? We will do the same thing as we did down here. However, it should not say t minus 1 here, but t minus 12. And of course, it's phi up there rather than 0.8. But what we'll get here is when we look, the first one here will be the same. But when you look at lag 1, and you have yt minus 12 here, plus epsilon t, comma yt minus 1. Well, epsilon t is in the future. And then you have, so that there's no covariance there. And then you have yt minus 1. Yt minus 12 and yt minus 1. There's no way you can get those to have, what we did here was to get to a point where we have the same time index. And then we know what we're doing. But you won't get that. So the only place where you start to get something is when you get to lag 12. So if you look at lag 12 for that process, you would have 0.8 yt minus 12 here and yt minus 12 here. So the solution is the same, just in lag 12 rather than lag 1. Can you guess what happens in lag? How far up do I have to go to get something again? (24) exactly. And the result is the same as here. So basically what we, I thought I had the slide including it. So the autocorrelation function for the seasonal AR12 model is only having stuff going on so the model that we have, let's just write the model. 1 minus phi of b to the 12th power on yt equals epsilon t. Of course, in lag 0, we get a 1. And then in lag 12, we get phi. In lag 24, we get phi square, 36, cubed, and so forth. So we basically have the same graph as before, except for the AR1 process, except that we only get something in the in-between lags. Now, when you multiply this with something that gives you something in the neighborhood, you will start to see tails around this. Okay, so the last topic for today is looking for predictions. So what we'll generally have is observation up to time t, and then we want to predict k steps out in the future. And as always, we want to minimize the expected square error. So the optimal prediction is the conditional expectation. Now, so we have the expectation of yt plus k given all the previous observation. That's what we denote as y hat t plus k given t. That's the compact notation that we'll use for this. The simplest case is the AR1 model. So let's get started there. It's already defined here. So I'll let the chalk up here. If we do it the more generic way, we just write a phi there and a phi there. So what is the expectation of this? Y hat t plus 1 given t. Well, we have to take the expectation of what we have over here. So it's the expectation t plus 1. Let me write it out. It's the expectation of, now we have to look at this time shifted one lag. So it's phi y t plus epsilon t plus 1 given y t comma all the previous y's. This is quite easy, right? What do we get? Expectation is a linear operator. So I can take each of the terms here one at a time. Expectation of phi times yt, given that you know yt. What is that? Sorry? Nope. I know yt, so it's just phi times yt. What is then the expectation of the epsilon t plus 1? Yes? 0, exactly. So we condition on something that we know. So this was an easy one. Now, if we want to predict further out in the future, we do the same thing. And then we will have yt plus 2 given t. It's a similar thing to this up here, but now I'll just write a little bit different. It's phi times y hat t plus 1 given t plus epsilon t plus 2. And we already calculated this value just before. So I get phi times what I have up here. So that I'll get phi square yt. And the expectation, I should write the expectation of the future epsilon, which is again 0. So whenever you step forward in time for the AR1 process, you get phi to the horizon that you predict. That's the power multiplied on the current value. So you do k-state predictions. Yes? We'll do that next week. Right now, we do not have any observations. We're just looking at the stochastic process, so we cannot optimize anything. But you will be doing least squares, yes. And as an example, this is what it would look like. You had a stochastic process, you observed it up to some time, and then you predict out in the future. Do you believe that is going to happen? No, because there is uncertainty. So what do you expect by intuition about the uncertainty? Exactly. The further ahead you predict, the higher the uncertainty. So we have to look at the variance of the prediction error. we look at the prediction error, which is the true value in the future minus our prediction. We just define our prediction like this. So what we need to go in and do is to use a bit of chalk. Looking at yt plus k, what is that actually? Well, the true value is phi yt plus k minus 1 plus epsilon t plus k. What I want to get down to something that is similar to yt. I want to get down to yt, because then I know what I have to deal with. So I will expand this yt plus k minus 1 in a similar way. So this is phi times, phi yt plus k minus 2 plus epsilon t plus k minus 1. So that is what I have there. And then plus the epsilon from before, epsilon t plus k. If I multiply this out, I get phi square yt plus k minus 2 plus phi epsilon t plus k minus 1 plus epsilon t plus k. If I repeat this once more, these are epsilons. I have to look at this one. I can do the exact same procedure as before. And I will just do dot, 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 skipping this line and go directly to what is similar to this one. I'll have a phi cubed yt plus k minus 3 plus what happened here was that I have a phi square. So I have a phi square on the epsilon that comes from t plus k minus 2. Phi square epsilon t plus k minus 2. And then I have what I had already from here plus phi epsilon t plus k minus 1 plus epsilon t plus k. Now I will repeat this k times, so that I get down to phi to the k power yt. That's what I wanted to get to, right? And then I will have a sequence of epsilons over here. I will have a phi. So this is the power k. Then the epsilon here comes with one less power. So I have an epsilon phi to the k minus 1 power of epsilon t plus 1 plus dot, 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 plus, and let's just take the last two terms from up here, phi epsilon t plus k minus 1 plus epsilon t plus k. What to notice is that the time difference here is plus 1 and k minus 1. The sum of this power and the time difference here is always k. K minus 1 plus 1 and k. So that's the one thing to keep in mind. So that's what we have. Now what we want to look at is yt plus k minus phi to the k power yt. So that is the term that we have here. So what we're left with for calculating the variance is the variance of this. So what is that? We have the individual epsilons here, they are independent. So we just have to look at the variance of each, the sum of the variance of the individual terms. So we'll get a variance so the variance of yt plus k minus phi to the k power yt equals the variance of phi to the k minus 1 power epsilon t plus 1 plus dot 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 plus phi times epsilon t plus k minus 1 plus epsilon t plus k. Each of these has variance sigma epsilon square. And when I take a constant and multiply that on something, and I want to calculate the variance of a constant times this, what do I get? What is the variance of this? I get a sigma square, a sigma epsilon square from this, and what do I get from this? Yeah, I square it, exactly. So I take phi of 2 times k minus 1 plus dot dot dot. Then I get a phi square, sigma epsilon square, plus a 1, or just sigma epsilon square. And if I write it in a more generic fashion, that's what I basically just did. Oops. I get, this is what we got, right? Phi 2 times k minus 1 to that power, and then phi to the 2 parentheses k minus 2 power, and so forth. The good thing is often you don't have to predict that far in the future, so you end up with mostly having terms down this end. And the prediction interval is the usual. You take a quantile. In this case, we know the epsilons. We know that they are standard normal distribution, so we don't have to consider the t distribution. We can just go to the standard normal distribution and look up the appropriate quantile and take the square root of variance because that's standard error. And then we have our prediction interval. If we are doing the same thing in an ARMA model, it's not as easy. Taking the ARMA model, written as up here, we use conditional expectation everywhere, and then we take all the y terms that are different from yt plus k, move that to the right-hand side. We have to look at how do we get around this. We need to know yt plus k minus 1. We need to know yt plus k minus p. What do we do? Well, we don't have them, so we need to calculate those first. So what we'll do is, recursively, we will first make a yt plus 1 given t prediction. There we will know everything if we filtered out our estimates of the epsilons, which we said, well, if the process is invertible, we can do that. We assume that we can do that. And then the next step is to get yt plus 2 up given t, and you can take one step forward at a time and get it done. It's a lot of work if you do it manually and if k is large. If k is small, it's doable. So one way to get around looking at this is to invert the process, as I said before, in order to estimate the epsilons. So we have to write the invertible form here. And the pi weights here should go to 0 sufficiently fast so that you can get a fairly good estimate of epsilon t with, say, the last 5 or 10 observations. That's usually sufficient. Then the weight becomes so small that it doesn't matter. Of course, it's not 100% accurate. It's an approximation, but it's a good approximation. And if you look at the variance of the prediction error, then we will write the whole thing on psi form. So here we move everything to be a polynomial in the y's in order to estimate the epsilons. Now that we get to look at the variance, we want to look at how are the weights on the previous epsilons. Sort of like what we did down here. We got it, the weight on the previous epsilons involved. And again, the procedure is the same. We have to look at the sum of square coefficients. Just the same thing that we did here for the AR1. There's a little bit more structure here because we have phi to the k minus 1, phi to the so forth power as being the size over here, but the structure is the same. So that's, and again, if we're doing a one-step prediction error, it's very, very easy to calculate. We don't even have to find the size because it's just a 1 times sigma epsilon square. If we want to do a two-step prediction error, well, then we need to find one coefficient. And we just have to figure out how to figure out what is the weight on the error one step backwards in time. Then we're good. We don't have to calculate the entire sequence of everything. We just have to go sufficiently far back. So start by identifying how far back do you need to go, and then go up and say, well, then I need to estimate psi 1 or psi 2 or whatever, and take it from there. A very brief example, just have a bond. We have someone who estimates a model. So we have this model up here with these coefficients. There's a mu mean value, and there's a sigma epsilon that's also estimated. How do we predict with this? First of all, which kind of model is this? It's an ARIMA model. So it's an ARIMA. And then I need 3 numbers in here. Can you see that? So it's an ARIMA model where you have the autoregressive order, then you have the order of differencing in the middle, and then you have a moving average part, the order of that on the right-hand side. You can just give any of the numbers one at a time if you know one of them. Exactly, 210. Because the autoregressive part here is of order 2. There's one level of differencing, and here we only have epsilon t, so there's no dependence on previous epsilons. So if we predict based on this, we have the price from the previous 6 days, and say we want to predict the price in 2 days from now. What we just learned is that we need to first make a one-step prediction, and then we can use that to make a two-step prediction. So what we'll do is we take the phi polynomial b here, and we'll get that by multiplying the 2 polynomials in the model together, like this. course, when we get into numbers, we will use the coefficients from here. But this is just a generic. So you have a second order polynomial with the first order polynomial, and you get these coefficients here in the third order polynomial that is the result of that. And then for the one-step prediction, you know yt, you know yt minus 1, you know yt minus 2. So that's easy. For the two-step prediction, well, now you have a prediction of yt plus 1, and you still know yt and yt minus 1. So that is also easy now. What is then left? We need to do one more thing before we're happy. So now we made a prediction of the value 2 steps ahead of now. What is the likelihood that I get that value? 0. So what do I need to do more? I need to do one more thing now. I need to look at the uncertainty exactly. So the variance of the prediction error, I have it down here. It's a variance of epsilon t plus 2 plus what comes from here is 1 minus phi 1 times epsilon t plus 1. Just by inserting the true value there and subtracting the 2, this is what I get out. And I get 0.499 square. And if I can do a prediction interval in the usual way. So that's doable. Here I actually did something different than what was proposed here. Well, I did it in a slightly different manner than what I said. I did not establish the psi polynomial as indicated up there. What I did do was to say, well, what is the variance of this is the, let me see if I have it. I started doing this, expanding yt plus k, and I got, you can say, this structure out as before. So I just need to identify the coefficients that I need. In this case, I'm only doing a two-step prediction, so I only need the last two elements here. So I need the phi square plus 1. So I have the 1 and I have the phi square, because 1 minus phi 1, that's the phi that I identified up here, well, actually up there. Right? Is that clear to everyone? Most, at least. It will take a little bit, quite a while to just go through the calculation hand by hand all the way through. But basically, if you look at this third order polynomial in B, you have it as 1 plus phi 1, or new phi 1, which is the old phi 1 minus 1. And what I have down here is our new phi 1 square. Right? So, rounding off for today, we kind of looked at the generic properties of stochastic processes and identified that if you take at a given point in time and look at stochastic process, it's a random variable. And if you get one realization, you define it as x of any point in time, comma, omega, where omega is the realization. We discussed stationarity. The definition of that is that if you're strongly stationary, the distribution function is invariant to change in time, or shift in time. And the autocovariance, here I wrote it correctly, subtracting the mean values of the process everywhere, but without loss of generality. We can subtract that first and then just play the game as if there is no mean value, which will make a lot of calculations easier down the road. Then we look at the moving average, autoregressive, and the combined ARMA models. We also look into the non-stationary models that is kind of made by taking ARMA models and doing some differencing and also doing seasonal models. So even though the polynomials in the P and the D are stationary and invertible as such, the process as such is not stationary. Because when you shift time, things are changing. And the optimal prediction is the conditional expectation. I had to have space for that when I did this. So that was all for now. That was my exercise for today. And I hope you'll spend some time doing the peer grading. I will send out a message on CampusNet in a moment with kind of where, if there are questions related to the peer grading, how should we do things? Is there any questions to that? I want you to just ask that, and I will answer that. And if I find the need for it, I will send out a message to everyone so you all get the answer. To do the peer grading, you do need to get a reference solution that I have. I won't show it now, because in case someone has not handed in, that are still going to hand in. So I will look at it, and then when I close, then I will close the hand in CampusNet soon, and after that I will send out a message with where is that file, so that you cannot hand in after that time point without getting permission from me. I think that's a fair way of doing it. My alternative is to send an email individually to all of you. I can also do that, but I'm afraid the spam filter will react. So I'll prefer to send out a message saying now it's available, here you are. Any questions? Okay.